Supervisory Control and Data Acquisition, SCADA, represents one of the most critical technological advancements in modern power system management. These sophisticated systems form the backbone of contemporary electrical infrastructure, enabling utilities to monitor and control vast networks of power generation, transmission, and distribution equipment from centralized locations. At its core, SCADA combines hardware and software components that work in concert to provide real-time visibility into power system operations while allowing for remote control capabilities that were previously impossible. The evolution of SCADA systems has transformed power utilities from reactive organizations that responded to issues after they occurred to proactive entities that can anticipate and prevent problems before they impact service reliability. This transformation has been particularly valuable as power systems have grown increasingly complex with the integration of renewable energy sources, smart grid technologies, and sophisticated distribution networks. Modern SCADA systems can process millions of data points per second from thousands of remote locations, presenting this information in intuitive interfaces that allow operators to make informed decisions quickly. In a power system context, SCADA serves as the central nervous system, continuously monitoring the health and performance of equipment such as circuit breakers, transformers, and feeders. It provides operators with the ability to remotely control operations like opening or closing circuit breakers and disconnectors, which dramatically improves operational efficiency and safety. The data acquisition capabilities of SCADA systems enable utilities to track performance metrics, identify emerging issues, and implement predictive maintenance strategies that extend equipment life and reduce downtime. Components of SCADA systems in power systems. A SCADA system in the power industry comprises several interconnected components, each serving a specific function in the overall architecture. The first critical component is the remote terminal units, RTUs, which act as the interface between field equipment and the central control system. These devices collect data from sensors, transformers, and breakers, converting analog signals into digital data that can be transmitted to the control center. RTUs also serve as the execution point for commands sent from operators, translating digital instructions into physical actions at remote locations. Sensors represent another fundamental component of power system SCADA implementations. Various types of sensors, including current transformers, CTs, voltage transformers, VTs, and temperature sensors, continuously measure critical parameters across the power grid. These sensors provide the raw data that forms the foundation of SCADA monitoring capabilities, enabling operators to track voltage levels, current flows, and equipment temperatures in real time. The accuracy and reliability of these sensors directly impact the effectiveness of the entire SCADA system. The communication infrastructure forms the connective tissue of SCADA systems, facilitating the transmission of data between field devices and the central control center. This infrastructure may utilize wired or wireless technologies, employing specialized protocols such as Modbus, DNP3, or IEC 61850 that are optimized for power system applications. The reliability and security of this communication network are paramount, as any disruption could compromise the ability to monitor and control the power system. At the heart of the SCADA system lies the Master Terminal Unit, MTU, which serves as the central processing hub. The MTU receives data from all RTUs across the network, processes this information, and presents it to operators through a human-machine interface, HMI. The HMI provides a graphical representation of the power system, displaying real-time data, fault alarms, and system status in an intuitive format that enables operators to quickly assess conditions and make informed decisions. Finally, the control system component enables operators to take action based on the data insights, implementing control commands that can isolate faults, restore power, or adjust equipment settings to optimize system performance. Why SCADA is popular in power systems. The widespread adoption of SCADA systems in the power industry stems from the numerous advantages they offer over traditional operational approaches. Perhaps the most significant benefit is the capability for real-time fault detection and isolation. Without SCADA, identifying faults in the power system often relied on manual reports from customers or field engineers, resulting in delayed response times and extended outages. SCADA systems automatically detect faults, isolate affected sections, and can restore power with minimal delay, often without human intervention. This capability dramatically reduces outage durations and improves service reliability for customers. Remote monitoring and control represent another key advantage of SCADA systems in power applications. Operators no longer need to be physically present at substations or other facilities to operate equipment, which enhances both safety and efficiency. This remote capability reduces human errors, minimizes exposure to hazardous environments, and allows for more rapid response to system events. During extreme weather events or other emergencies, when physical access to facilities may be dangerous or impossible, SCADA systems enable utilities to continue managing their infrastructure effectively. The data-driven decision-making capabilities enabled by SCADA systems have transformed power system operations. By providing operators with real-time data on voltage levels, currents, temperatures, and other critical parameters, SCADA allows for more informed operational decisions and proactive maintenance strategies. Utilities can identify trends that indicate developing problems before they result in equipment failure, implementing preventive measures that extend equipment life and reduce maintenance costs. This data-centric approach also supports better load management and more efficient utilization of existing infrastructure. Safety improvements represent another compelling reason for SCADA's popularity in power systems. By allowing remote control of equipment, SCADA reduces the need for operators to enter potentially dangerous environments such as high-voltage switchyards or substations. This not only protects personnel from electrical hazards but also reduces the risk of accidents during maintenance operations. The ability to remotely de-energize equipment before personnel arrive for maintenance further enhances safety protocols. Finally, the automation capabilities of SCADA systems have made them indispensable in modern power operations. These systems can automatically perform routine actions such as switching equipment on or off based on predefined conditions, minimizing the need for human intervention and reducing response times during system events. This automation not only improves operational efficiency but also ensures consistent application of operational procedures, reducing the potential for human error. Security challenges and future trends. Despite their numerous benefits, SCADA systems in power applications face significant security challenges that utilities must address. Many SCADA systems were originally designed for isolated environments without consideration for cybersecurity threats, resulting in inadequate authentication mechanisms and other vulnerabilities. The use of proprietary protocols without encryption further compounds these security issues, making data transmissions susceptible to interception and manipulation. Legacy systems with unpatched vulnerabilities present additional risks, as does insufficient network segmentation that can allow attackers to move laterally across systems once they gain access. To address these challenges, utilities are implementing comprehensive security strategies that include multi-factor authentication, adoption of standardized protocols with built-in encryption, regular vulnerability assessments, and network segmentation. Many organizations are also implementing virtual private networks, VPNs, and end-to-end encryption to protect data in transit. The increasing integration of SCADA systems with enterprise networks and the Internet has heightened the importance of these security measures, as the potential attack surface has expanded significantly. Looking to the future, several trends are shaping the evolution of SCADA systems in power applications. Edge computing is emerging as a key trend, with intelligence being embedded directly in sensors, controllers, and local HMIs rather than routing all data to centralized servers. This approach reduces latency in time-sensitive operations and decreases bandwidth requirements for remote sites. Artificial intelligence and predictive analytics are also transforming SCADA systems, turning raw operational data into actionable insights that enable predictive maintenance, anomaly detection, and energy optimization. Cybersecurity is becoming increasingly central to SCADA development, with zero-trust architectures, multi-factor authentication, and end-to-end encryption becoming standard features. Cloud-native SCADA solutions are gaining momentum, offering 24/7 access from any device, easy integration with other enterprise systems, and scalable deployment across multiple sites. The convergence of SCADA with industrial IoT, IIoT, is creating unified platforms that can integrate thousands of sensors and provide customizable dashboards for different stakeholders. These technological advances are positioning SCADA systems to play an even more critical role in the future power grid, particularly as utilities transition to more distributed generation resources and implement smart grid technologies. The continued evolution of SCADA will be essential to maintaining reliability and efficiency in increasingly complex power systems.